Okay, so we're going to go over vertical asymptotes, and we're going to specifically focus on these rules here. The graph of f at x has a vertical asymptote when x is equal to c if any of the following is true. The limit as x approaches c from the left is a positive number, or is heading towards positive infinity. The limit of f at x when x approaches c from the left is equivalent of negative infinity, so that means it's approaching positive, and this here is approaching negative infinity. And this vice versa from the right, the exact same idea. So the idea is that if we ever get anything that does this, anything that does that, anything that does this, and anything that does that. Okay, the line in the middle being our vertical asymptotes. So this is very similar to when we were going over limits. What we're going to be doing is looking for when a function will become undefined. So in this question here, the very first example, we have f at x is equal to x over x squared plus x minus 2. We're looking for when the bottom of this equation would be equivalent to 0. When it become equivalent to 0, we'd have an undefined equation. So what we're going to do is we're going to factor this to see what values of x would give us 0 in this equation. So we only have to really focus on the bottom part of this equation right now. So we're going to take a look at when f at x, x squared plus x minus 2 is specifically equal to 0. We'll factor this, and when we factor it, we're going to get positive 2, negative 1. So x plus 2, x minus 1 is equal to 0. We know that if either of these are equal to 0, the entire equation will equal 0. So we set both of them equal to 0 to see what our options are. We have 0 is equal to x plus 2. 0 equals x minus 1, which means x is negative 2 and x is 1. So at either of these values, we'll have an undefined equation. We also know that they will give us values on top for an x, so we don't have to worry about any holes or anything like that in the equation right now. So our undefined values are negative 2 and 1. So what we're going to do is we're going to set up, again, a number line. And we're going to be looking at intervals. Now specifically, it's a little different how we did it last time when we were talking about increasing and decreasing derivatives. We have the value of negative 2 and 1. And what we're going to do is as we approach, so as the limit approaches negative 2, so say our value is as x approaches negative 2 from the left. So we're going to be looking for values that are infinitely close to negative 2 because we know the limit doesn't exist at negative 2. So maybe a value like negative 2.001. We're also going to look at the same idea of the limit when x approaches negative 2, but from the right this time, which means we're going to be using a value, and I'll write the values below, 0.0001. We'll be using like a value of 1.9999 to see what our f at x equals in this case. Negative, thank you. Thank you. In our other example, same idea, we know that we have, our limit doesn't exist at 1, so same idea, we'll be approaching 1, so the limit as x approaches 1 from the left, so a value like 0.99, and the limit when x is approaching 1 from the right, so a value like 1.0001. So what we're going to do is we're going to plug values in. Now luckily we're already in factored form, so it'll be easy for us to decide what our y value is going to be. We should be finding y values, okay, assuming these are vertical asymptotes, that will either approach negative infinity or positive infinity at these points. So we have one of two options. Whoops. So remember our f at x was equal to the value of x, and we'll leave it in our factored form, x plus 2, x minus 1. What we're going to be really looking for here is our positive and negative values and how large the numbers will become. Okay? So in this case, we're looking for a value where if we were to plug in negative 2.001. So if we were to plug this in, f at negative 2.0001, we have negative 2.0001 over, here we're going to get a infinitely small negative value, so we have negative 0, 0, 0, 0, 1. Okay? And over here, we would end up with negative 3, 0, 0, 0, 1 in our question. When we go to multiply these, what ends up happening is we have approximately negative 2, 0, 0, 0, 1, let's say, over our value here. And our value is a positive term of 3. What is it? Oh, sorry, not 3. Yeah, extremely small value, okay? So negative 0.000, probably 3-ish, okay? Oh, thank you. So it's positive. So what this does is this makes this a negative equation, okay? Oh, and I wrote positive there. This makes this a negative equation in the end. And this negative equation, as we're going down, is letting us know that we will start to approach a negative value as we go through this. So as this value becomes greater and greater, these values become smaller and smaller. So we start to approach our negative infinity at this point. Okay, so at our first interval, our graph towards the vertical intercept, or asymptote, sorry, is approaching negative infinity. We do the same idea with our negative 1.999. Okay. So again, we're going to focus on the positives and negatives without the numbers this time. So we have our f at negative 1.999. Okay. And what we're getting here is we have a negative value, so we'll focus on that. I'll write the numbers in. When we do negative 1.999 plus 2, we have a very small positive value. And when we have negative 1.999, yes, we get a very small 2.999 value. Okay. So here, we get a negative and a negative. So we'll have a negative on top. And our positive times a negative gives us a negative on the bottom. So we end up with a positive value. So our positive value is informing us that when we are approaching this limit from the right, we are actually approaching positive infinity at this point. Okay, and I should do those in different colors, I suppose. So we're approaching positive infinity from the right, and we're approaching negative infinity from the left. We're going to do the same process over here when we're approaching our value of 1. This time really focusing on the positives and negatives. So our f at 0.999. Okay. We know we have an x on top, so I'm putting a positive value in on top. And I'll write the two numbers in here just so I don't forget them. X plus 2, x minus 1. X plus 2, and x minus 1. When we plug in 0.999 into here, we get a positive value. And when we plug in 0.999 here, we end up with a negative value. So we'll have a positive times a negative, which will give us a negative on the bottom, which means when we divide these two terms, we have a negative value, which means we're again approaching negative infinity when we're approaching it from the left. So in this case here, same idea. We're approaching negative infinity when we're getting closer and closer to this vertical asymptote. And we'll do the same thing from the right. F at 1.0001. On top, we have a positive value. Okay. When I add 1 to this, this will become a positive value here. And because it's greater than 1, this will also be a positive value. All these positives will just be a positive divided by positive, which means we have a positive answer. So our vertical asymptote in this case, when we approach it from the right, we're approaching positive infinity. So if we were to make a rough sketch of this model with our vertical asymptotes, we know we have a vertical asymptote at the value of negative 2 and a vertical asymptote at the value of 1. We'll put two lines representing those asymptotes. So at negative 2 we have a value, and at 1. And according to our information, as we go across, when we approach it from the left, we're going towards negative infinity. When it's approaching it from the right, it's heading towards positive infinity. Now, because there's nothing in the middle here, we go on the assumption that this is eventually turning at one point and coming back down because, again, when it was approaching positive 1 from the left, it was approaching negative infinity. And from the right, it was approaching positive infinity. So this would be an example of a rough sketch of our model with our vertical asymptotes.